Okay, class, let's continue with our second hour of this today's sessions. Now, for this second hour, I think I would like to go through with you another method for drawing shear force and bending moment diagram. Now, yesterday class, we have already covered one particular method, which is the method that you have learned, and which is a section method. Now, class, that is the most basic method, and that you should master that method in order for you to be able to calculate internal forces, and also after that, and then get the equations for the shear force and bending moment variation for different portion or different parts of the beams, and later on for frames, and then later on draw them together. Draw them at the end for shear force diagram and bending moment diagram. So it is very important that we know the steps involved, which is first to get the reaction forces. Then after that, decide how many cuts, minimum number of cuts that you need to do, and where to cut. Where to cut means which part of the structures you need to cut a section within them. And after that, for each of the cut sections, then you calculate the shear force and bending moment. Calculate the shear force and bending moment. And remember, class, the sign conventions. When you use the right-hand side of the cut or right-hand side of the cut, left-hand side or right-hand side of the cut, use the correct conventions for shear and bending moment, so that at the end you get consistent result for shear and bending moment. It doesn't matter which part you use. You get the consistent result, the magnitude is consistent, and the sign, positive, negative, also consistent. Then the important part is knowing how to draw the shear force and bending moment diagram. And there are some characteristics of the shear force and bending moment diagram, which is associated with the type of loading, the type of support that you need to take note of, so that you can judge whether the shear force diagram or bending moment diagram, which has already been drawn or which are given to you, is reasonable or not. Okay. So in drawing shear force diagram, bending moment diagram is always good to indicate. I think when you draw the name of that diagram, shear force diagram, SFD, and the unit, you can lump it here or you can put it directly in the diagram. Positive, we put it on the top of this line representing the beam. Negative, we put at the bottom. Then, okay, and bending moment diagram, the same thing. We put bending moment at the top, positive at the top of this line, which representing the beam. And if it's negative value, it goes to the bottom of that line. And give the name to that diagram, bending moment diagram, short form BMD. The unit, again, you can lump it here or you can put the unit directly in the diagram itself. Okay. So these are the things that we have gone through. We have gone through. Now, there is another method that it can help us to draw shear force diagram and bending moment diagram. And this method is what we call so these are some of the things that we have covered. I think the characteristics of shear force diagram and bending moment diagram, which you must be able to relate to, so that you can use to judge the shear force diagram, bending moment diagram, whether they are drawn correctly or not. Okay. Now, today we would like to look at one method, which is for drawing shear force and bending moment diagram using the relations between loading and using the relations between loading diagram and shear, and then after that using the relation between shear and bending moment to draw the diagrams. And these methods can speed up the drawing of shear and bending moment diagrams. So the basic idea here is that we make use of some basic relations starting from loading diagram. Loading diagram is actually the problem given to us, and we specifically look at whether there is any distributed load, whether there's any point load, and then we make use of some relationship that I'm going to show you where do they come from. Then make use of that relationship, we get from loading diagram, get the shear force diagram. And after that, use again another set of basic relations relating shear and bending moment. These two set of equations, then we get the bending moment diagram. So this is another method which is alternative to section method. But section method is the most basic method because it makes use of equilibrium only and our understanding of free body diagram and the correct convention of shear, bending moment, and axial force later on. So this method is what we call the method of direct integrations. Direct integrations. So let's look at where does those equations, basic equation, come from. So I show you here the slide here, one general beam subjected to loading distributed load. This is distributed load, and here it is shown as positive upwards. So in our derivations of the basic equations, we assume distributed load positive as upwards. So later on, if the distributed load is acting downward, so we have to substitute value as negative. We also look at this point load, which is positive as upward as positive. And if there is a concentrated moment acting at a particular point, we look at this clockwise as positive. Clockwise as positive. This concentrated moment, applied moment, not the bending moment. Then we will look at this free body diagram one by one here, this free body diagram one by one here to get the basic equations. This free body diagram is cut from a small portion here where the distributed load is acting. So this is a free body diagram, and this free body diagram is cut just to the left or just to the right. And just slightly to the left or slightly to the right here, a very small portion here where the point load is acting. And also the third one here, the free body diagram, is a small section cut out at the section slightly just to the left and just to the right of this where this concentrated moment is acting here. So to differentiate this moment from the bending moment, we put a bar above this moment to represent that this is applied moment. This is not the internal forces of the moment. This is applied moment here. Okay. Now we start with the first basic equations. To get our aim is to get the basic equations between the distributed load W and the shear force. So by using this free body diagram, then by taking the summation of forces in y direction, so we have S plus W dx. This W is assumed to be constant over this small distance, so the equivalent load is W dx going up. And then come to this side, we have an increase in shear because the shear will generally change. And sometimes it's constant, but in general, we can consider the shear will change as you move along the axis of the beam. So there's a change in shear. So ds here is a change in shear. So we make them equal to 0, then we get these first basic equations. So these first basic equations I show again here on this slide. So ds dx equal to w. So this equation means the slope, ds dx in calculus class, we remember dy dx is a slope. Slope of what? Slope of a point in the shear force diagram, because S is shear here. So slope of a point in the shear force diagram is equal to the intensity, is equal to the intensity of distributed load at that point. Now remember, W is considered as positive upwards. So this equation means that the slope of shear force diagram at the point here, the slope here, is equal to, if you look back at the corresponding point in the beam, the loading diagram itself is equal to the intensity of distributed load at that point. So this is the first important basic equations relating shear and distributed load. Now we go to the second set relating shear to bending moment. So here we take bending moment at A here. So there is a bending moment M. We take this as clockwise as negative. So come to this side, we have increment in M. So bending moment also in general will change. So change in bending moment M plus dm. Then this small part here, so this is treated as a uniformly distributed load. So in this small part, this is assumed as constant. So W dx multiplied with dx over 2, this is a moment caused by this W at A here. And it is counterclockwise direction, so become positive. And then finally, this shear here, this one will cause moment at this A here. So S multiplied with ds, S plus ds multiplied with dx is the moment, and it is clockwise, so we take this as negative. So summation becomes 0. And if we try to summarize this, I think simplify this, then we get to equation like this. Okay, we get the equation like this. So this one, W multiplied with dx squared. So these terms, we neglect this because dx is a very, very small value, a very small distance only. And if we square again, it will become even smaller. So negligible. This value compared to the rest of these terms is negligible. And also this part here, ds multiplied with dx, this is a very small value, multiplied with another small value. Again, this is negligible. So we neglect this. So as a result, we come to these equations, which is relating shear and bending moment. So shown here is the second important relations that we need in this method for draw shear force diagram and bending moment diagram. It is dm dx over s. So dm dx, this is from calculus, is the slope of bending moment diagram at a point is equal to shear at that point. So I show you in this diagram, the slope, this is a bending moment diagram. So the slope of a particular point, the red color here in the bending moment diagram, is equal to the shear at that point. So if this is positive shear, so the slope is positive. And the same thing, the purple point here, the slope in bending moment diagram at that point is equal to the shear at that point. If that shear is positive, then the slope is positive. So this is the second important set of equations, important equations relating bending moment and shear. Now, first, now let's look back this first set of equations that we derived, which is relating the slope in the shear force diagram to the distributed load, intensity of the distributed load at that point. This is the first set of basic equations that we have derived. And if we rewrite this in this way, and then finally we can come to these equations, which is integrations. We rewrite this in this way, and then we integrate this from one point A to point B. And from calculus, we know the integrations from one point A to point B is equal to the difference of the value in S between point B and point A. This is from definition of calculus from integrations. Integrations of S, of a curve S, is equal to the difference between the value at point B and point A, which is SB minus SA. And that one is equal to the area under the loading diagram between point A and point B. So these equations here, SB minus SA equal to integration AB W dx. It means that change in shear between points A and B. So SB minus SA is a change in shear between points A and B, is equal to area under the distributed load diagram between points A and B. So now I'll show you in the diagram form, if I have a loading diagram. This is actually the problem given to us, and we first look at the loading diagram. So this shows the distributed load acting between A to B, between A and B, between A and B. So the equation, this one means that the area under this, the difference SB minus SA, the difference between the shear at this point A and point B, which is SB minus SA, is equal to the area under this loading diagram, under W here, between A and B, the green color here. So this is the meaning. Integration A to B W dx is equal to the area under this loading diagram, under this W diagram here. And the slope, so slope in this shear force diagram is equal to the intensity of W at that point. The intensity of this distributed load W at that point. So this is the first set of equations that we need in order to get shear force diagram from what we call loading diagram. Now, after we get shear force diagram, we can get bending moment diagram by using these two relations here. So here I emphasize again, the slope in the shear force diagram is equal to the intensity of this distributed load at that point. If it is upwards, then the slope becomes positive. If it is acting downwards, then let's say -2, then the slope becomes negative. The second set of equations is coming from here. The dm dx is equal to S, and we integrate from A to B. Then we get MB minus MA. Then we get this integration from A to B, the shear force diagram. So this means that the change in bending moment between A and B, this is change in bending moment now, is equal to what? Area under the shear force diagram between points A and B. So let's show in diagram form again. We have obtained shear force diagram, and the area under the shear force diagram between A and B is this red color here, red dotted color here. This is area under the shear force diagram between A and B. So the equation that I show you in the previous slide, it shows that the difference between bending moment between point A and B, which is MB minus MA, or the change in bending moment. We call it the change in bending moment between points A and B. The change in bending moment between point A and B, which is AMB minus MA, is equal to the area under the shear force diagram, the red color here that I dotted here, the area under the shear force diagram between point A and B, And the slope of the bending moment diagram at the particular point is equal to the corresponding shear at that point. So this is the set of equations that we need to get bending moment diagram from shear force diagram, Now, these two sets of equations that I have shown you just now, relating the loading and the loading diagram and shear force diagram, and then the second set relating the shear force diagram and bending moment diagram, cannot be applied. We cannot apply this when there is a concentrated load. When there is a concentrated load and when there is a concentrated moment. So these equations, which is relating the loading, distributed load to shear, the slope in the shear force diagram, and this is relating the change in shear force between point A and B, and the area under the loading diagram is not valid at point C here. It's not valid at point C here. We must do something. We must do some extra process before we can apply these basic equations. It's not valid. And the set of equations which relating the slope in the bending moment diagram to the shear, also the change in bending moment between point A and point B in the bending moment diagram, and the area under the shear force diagram between point A and point B, this is not valid at the point where there is a concentrated moment acting. So in the solution process, when we see there is a concentrated load, when there is a concentrated moment, there's extra process that we have to do. But those equations which is relating to shear, okay, between W and shear, this set of equations is valid at point D, where the concentrated moment is acting, and Similarly, those set of equations which is relating bending moment and shear, this set of equations is valid at point C. Is valid at point C. So what does it mean? After that, when we go through example, so we will see what does it mean by not valid. So it does not valid means we cannot directly apply these two set of equations in the process of getting the shear force diagram and bending moment diagram. We need to do extra steps before we can make use of these two set of equations. And then extra things is we need to realize that there is a jump. There is a jump in shear force whenever we encounter concentrated load. So shown here is one particular section that we cut from when we cut up from the beam where there is a concentrated load acting. This section is slightly just to the left and this section is slightly just to the right. So when we say that the basic equation relating the shear and loading diagram does not apply here, meaning that we have to realize that there is a jump in shear force before and after a concentrated load. So this one can be shown by using these equilibrium equations here. We consider, force equilibrium equation, then we get to these equations. This equation means there is a change in shear at the point of application of point load. And that change in shear, when you move just slightly to the left of this point, and then we go to slightly to the right, when you move through this concentrated load, there is a change in shear, and that change in shear is equal to magnitude of the point load. Magnitude of the point load. Here we assume going up as positive, so there is a positive change. If this P is acting downward, so the change becomes negative, which means the shear will go to, the change is negative. Same thing if at the concentrated moment, if you look at the section before and after, slightly before and slightly after the point of actions of the concentrated moment, then from this equilibrium equation, we can see that there is a change in bending moment at the point of application of a couple or concentrated moment, and the change, the M change to dm here, the change is equal to the magnitude of the couple itself. Here we consider clockwise as positive change. If this is anti-clockwise, then the change becomes negative. The change becomes negative. So this is the reason why we say that the basic equations relating to W and S is not applicable at the point of action of concentrated load, because there is a jump. There's a jump in shear force when we move before and after the load. Similarly, when we say it is not applicable, the basic equation relating moment and shear is not applicable at the point of actions of applied moment or couple, is because there is a jump in the bending moment when we consider the section just to the left and section just to the right. So there is a change in bending moment at the point of application of a couple, and there is a change in shear force at the point of application of a concentrated load. And we need to do something, we need to consider these changes before we can proceed using the equations that we have shown you just now. Now, let me pause here for a while and then